All right, so this is going to be a long video. I'm going to do the entire introductory chemistry PowerPoint. I know you guys are getting some of this in class, some of this at home, so you don't have to sit here and watch the whole video if you don't need to. Just make sure that you're watching the parts that you're not getting at home, okay? So if you have questions at the end, shoot me an email. In the middle, shoot me an email, whatever. But I'm just going to go through this, and that way you will have it all in one place that you can turn back and refer to. All right, so let's get started. So you are in inorganic chemistry. This is kind of the intro PowerPoint. It's going to talk to you, as it says, about what it is and what it is not. All right, so basically, let's see if I can get my PowerPoint here to work. Chemistry is the study of matter. All right, it's the study of what matter is composed of, how it's structured, what properties it has. Right? It studies the changes and the processes that matter can undergo, right? And it studies the energy that is required to, get those changes to happen. Now, another way to kind of put it is it's the study of everything and how it interacts with everything else. So chemistry is often called the central science because you find chemistry in pretty much every single branch of science. I mean, it touches in some way, shape, or form on everything, all right? And we'll talk more about why later on. Now, there are a lot of different branches of chemistry. Here are just a few, okay? Physical chemistry studies properties and changes of matter and how that relates to energy. Analytical chemistry goes into how to identify unknown compounds. Theoretical chemistry is, computer-based chemistry, computational chemistry, that uses concepts and principles to model behavior and predict how new chemicals might act. One of the more interesting things from that is actually buckyball, which is 66 carbon atoms that are arranged like this. You can see it in that picture right there. And a lot of theoretical chemistry and physical chemistry went into the development of this molecule. This is a man-made molecule, okay? Biochemistry is another branch of chemistry that has huge impacts on us as human beings, right? It covers all of the things you talked about in biology, like macromolecules and enzymes and activation energy, but also, your medicinal chemistry and pharmaceutical chemistry comes from our understanding of biochemistry. The two branches that we're going to talk about a lot are organic chemistry and inorganic chemistry. Now, officially, you are in inorganic chemistry, all right? But at the very end of the year, we will reach into organic and just kind of talk about a few basic concepts that come from that class. Basically, organic chemistry is the study of carbon chemistry. So buckyball, or its full name is Buckminster fullerene, is an example of a carbon compound. So it would be organic chemistry. It's a polymer. Inorganic chemistry is the chemistry of metals and nonmetals bonded together. That is the primary thing we'll study. So salts, anytime you have a metal bonded to a nonmetal, it's called a salt. So table salt is a great example of inorganic chemistry. We also look at nonmetals bonded to other nonmetals. So water is hydrogen bonded to oxygen. Those are two nonmetals, and we will look at those as well. Now, why do you need all these branches? Well, basically, chemistry is a research science. So in research, you have basic research and you have applied research, and different branches are going to fall under different forms of research. So, applied research would be like analytical chemistry. We're taking, concepts and we're using it to investigate an unknown chemical. If you're in like theoretical chemistry, well, that'll be basic research. So we're looking at the how or why behind a reaction. We're trying to identify properties. And a lot of times the two overlap, okay? You can't really do basic research without some application. You definitely can't do application without some basic research. So they definitely go hand in hand. Both lead to what we call technological developments, okay? And that's just something that enhances our quality of life. Computers would be a technological advancement. Catalytic converters, not convertibles, that are part of your cars, definitely technological advancement. Biodegradable plastics, definitely an advancement. Buckminster fullerene, all right? One of the things that they're looking at is if they can put a medicine in the middle of this compound, right? So like right down in here, have a medical compound in there, and then you use this as a pill. You take it, and then as it decays in the body, you get time-released medication. So those would all be examples of technological developments. And the list goes on. There are many, many, many. All right, so that's kind of the basics. Now let's look a little closer at like what chemicals actually are. So a chemical is just any substance with a definite composition. So that means its composition is defined by a set number of atoms of a set number of elements. So glucose is a chemical. Glucose is always C6H12O6. You should have learned about that in biology when you did ATP and you did photosynthesis. Water is a chemical. It's always H2O. Carbon dioxide, always CO2, right? Buckminster fullerene, right? Our big C66H100 and something. All right, it's always carbon and hydrogen, okay? So that's a chemical. It's just a substance with a definite composition. Just for your information, all right, the number one chemical made every year in the U.S. We make billions upon billions of these chemicals, okay? Millions of tons. Sulfuric acid is the number one every year. You use it to refine petroleum. It's used to etch metals. It's used to make fertilizer. I mean, it's really important. Ethene, pretty big chemical that we produce. It's actually used to ripen fruits. So, if you use an ethene scrubber, you can kind of freeze or suspend the ripening of a fruit, pick it, put it in your container with an ethene scrubber, ship it across the country, take it out, spray some ethene on it. It'll start to ripen again, put it out, sell it, So big business in the production of chemicals every year. And again, these are just some examples. You don't need to know them, just do how you measure on a day-to-day basis. Now, since we are talking about the study of matter, okay, we got a couple things we want to make sure that we can do by the end of this. We want to know the difference in a chemical property and a physical property. We want to be able to classify a change as a physical change or a chemical change. We want to explain particle movement and compare how they move in solids, liquids, and gases. Okay. We want to look at the law of conservation of energy and be able to define that, describe it, maybe give an example of when it is in effect. And we want to make sure we know the difference in a mixture and a pure substance. So that's the next about 20 slides or so. So let's get into that. So matter is anything that has mass and takes up space, right? Now there's a really corny chemistry joke that goes along with this, which I'm going to tell you because it's going to help you remember it. So if you have mass and you take up space, then you matter. And that is a really corny chemistry joke, but it's good. It points out, hey, matter is anything that has mass and takes up space. I will tell you a lot of really corny chemistry jokes throughout the year because I think they help and because I like them. So deal with it. Now, when we look at matter, we usually define it into solids, liquids, and gases. Now, we define those things with how they behave in terms of shape and volume. So a solid holds its shape and has a fixed volume. So like this metal coffee cup, right? It's a solid. I don't have to worry about sitting it down and the shape disappearing, right? Becoming flat on the surface or something. It's going to hold its shape. So it's definitely solid. There's coffee in this coffee cup. I don't know if you can hear it, but it's a liquid and it's going to take the shape of its container, but the volume is fixed. I'm not going to come back later and find that it's all of a sudden taking up more space than it was before. A gas, on the other hand, it's going to take the shape of its container, which means its shape is not fixed, and it's going to take the volume of the container, which means its volume is not fixed. If you put gas in an ever-increasing container, it will continually expand. Mass measures the amount of matter. We use grams or kilograms or milligrams to measure mass, and volume measures the amount of space it takes up, and that's in 3 dimensions. So those units will be cubed. So if you have cubic centimeters, or if you had cubic inches, or like if you order concrete in America, it usually comes in cubic yards or cubic feet or yards. If you see a cube dimension, it's probably referencing volume. And that's because it takes 3 measurements to figure out how much space something takes up. You need length, width, and height, right? So 3 measurements, you get a cube unit. Density relates mass and volume. So you need to know the formula for density for chemistry. It's density equals mass divided by volume, or D equals M over V. And because we are dividing mass by volume, and those two units don't cancel out, right? Then the units for density are just grams divided by milliliters, or whatever unit they use for volume. So if you were using English units, right, the imperial system, you could say like pounds per cubic foot, or you could say pounds per, or ounces per, what would it be? Gallon, ounces per gallon. That would be density. That would be a really weird unit, but you could do that. We don't do that in chemistry. We use the metric system. So we would say, kilograms per liter or milligrams per milliliter. That's a really common one. We usually call that mgs per mil. Mg over ml is mgs per mil. All right. Now, there's 4 states of matter, right? Solid, liquid, gas. We talked about those. There's also plasma. Okay, plasma is an ionized gas. And just like we want to be able to look back here and, kind of look at how they behave in a shape, or how they behave in a container, whether they hold their shape or they don't. We also want to be able to describe that in terms of the molecules. So this is a really important slide. Make sure you understand this slide, all right? In a solid, okay, the molecules are packed into an organized arrangement, a crystal, right? So they overlap, they're locked in place, and they do vibrate. They move a little bit, all right? Molecules are always moving, but they hold their shape and they don't move, okay? They don't slide past each other. In a liquid, all right, there is, sliding occurring. The molecules are moving past one another, okay? And they're holding their, self together. Their volume isn't expanding, but their shape is fluid. In a gas, both the volume and the shape are not working out. So, they're bouncing off each other and they're constantly spreading out and they're moving erratically, right? And we want to be able to describe how a solid moves compared to how a gas moves, how a liquid moves, right? So make sure you can do that, right? In a nutshell, solids are locked in place, liquids slide past each other, and gases bounce off and move erratically. That's the kind of boiled down version. Not only do we want to be able to describe it, we also want to be able to classify it. So we can put matter into 2 basic categories. Matter is either a pure substance or a mixture. We can then further break those down. So in the next couple of slides, we'll look at that, but we want to be able to make sure we can classify matter. So we want to be able to describe how it moves. We want to be able to describe it, as a fixed shape or a fluid shape, something like that. We also want to be able to classify it. So let's look at that. A pure substance has a fixed composition, right? And it's not going to change. So nitrogen is N2, chlorine is Cl2, right? Lithium is just lithium. It doesn't form as a dimer, or dimer is 2 parts. So chlorine is always a dimer, nitrogen is always a dimer, oxygen, hydrogen, they're dimers, but like lithium is not a dimer. If you are a pure substance, then let's say you had pure nitrogen. Saying you have pure nitrogen, that means that your container, right? So this is full of nitrogen. Nothing in this container is not N2, right? It's just pure nitrogen. If you look at the things that I have in the chemical closet that we'll pull out and use, these are pure substances, okay? And they are, uncontaminated. They are, a certain percent pure. And if you look at the, qualifiers or adjectives they use to define the grade of purity, most of the things that we have are ACS. They're American Chemical Society specified reagents. I have 1 or 2 primary standard reagents, but they're pretty expensive. Now, something that I think is interesting, in order to put something in a food, it's way down here, right? Barely above industrial chemicals. But in order for me to use something in the high school chemistry lab, we're all the way up here. So just kind of shows you what's more important about purity of your chemical, right? Now, when we look at, pure substances, and we're talking about, the fact that they consist of an element or a molecule, right, a compound, we need to talk about an element. So elements are made of atoms. We're going to spend a lot of time this year talking about atoms. because an atom is the smallest unit of an element that still acts like that element. It still keeps its identity. Okay, so kind of similar to last year in biology when you learned that cells were the smallest components of living things. Atoms are the smallest components of elements. Okay, and elements are the building blocks of compounds. Now, a compound is two or more elements bonded together. Actually, two or more atoms bonded together. Because oxygen, O2, is a compound. It's, two oxygen atoms bonded together. Okay. When you look at the other side of our pure substance, we have the mixture. And a mixture is a blend of two or more different kinds of matter. Now, the difference between a compound and a mixture is pretty simple. In a mixture, the compounds keep their identities. You can separate them and, still have them together. So like salt and pepper. If you mix salt and pepper together, okay, it looks like salt and pepper. You can still see the pepper's black, the salt's white, the salt looks like a crystal, the black looks, the pepper looks like black little flakes. You could separate those and get, salt and pepper back. They keep their chemical identities separate, even though they're mixed together. In a pure substance, if you have a compound, well, that's not necessarily true. If you have carbon dioxide, which is carbon and two oxygen atoms, well, it doesn't act like carbon mixed with oxygen. Carbon mixed with oxygen would be like graphite sitting out in the air. Those are two very different things, right? So graphite mixed with oxygen acts like graphite and oxygen. That's a mixture. But carbon dioxide is a compound that acts completely different than the two substituents. So when we're looking at mixtures, we're looking for things that retain their identities and their properties. There's two kinds of mixtures. You can have homogeneous mixtures, has the prefix homo, means the same. We usually call them solutions. So a homogeneous mixture and a solution, those two words can be used interchangeably. They are uniform. They look the same throughout. So like salt water is a great example of a solution. You can't see the salt. It doesn't settle to the bottom, right? It just looks like water. Then you taste it and you're like, oh, that's disgusting, right? Sugar water would also be a solution, okay? Coffee would be a solution. Anything that is uniform in composition looks the same throughout, okay? Is a homogeneous mixture. On the other hand, you have heterogeneous mixtures. Hetero means different, so they don't look the same throughout. Italian salad dressing is a great example of a heterogeneous mixture, okay? Because if you leave it sitting there, it settles. Muddy water, great example, right? If the mud is clay, you leave it sitting there, it settles to the bottom. You step in it, you get the big cloud of clay that comes up, but eventually it settles back out. Okay, so that's the big difference between homogeneous mixtures and heterogeneous mixtures. Here would be two heterogeneous mixtures, right? You would think, all the redheads at this redhead convention, which I don't know why there's a redhead convention. Maybe they're, trying to bond together as redheads. I don't know. Anyway, you would look at, they're all redheads. Well, not really. It's not the same throughout. Some of the redheads are darker, some are not. Over here on the right, you have all these different colors mixed together. Those are definitely heterogeneous mixtures, okay? It's really hard to find a picture of a homogeneous mixture because it looks the same throughout. Like, I could put up a picture of a glass of water, but that'd be kind of boring, right? Look, a picture of a glass of water. Ugh. Yeah, so on the left, we have homogeneous. On the right, we have heterogeneous. So we're really just trying to identify things based on our observations. If it settles out, probably heterogeneous. If it looks uniform, probably homogeneous. Now, switching gears a little bit, looking at properties, okay? Because we also said that chemistry studies the properties of matters. There's two kinds of properties. There's extensive and intensive properties. Extensive properties depend on the amount of matter that's present, okay? The volume, the mass, the energy, and the substance, these things all depend on how much matter is there. So if I have 40 grams, that's a mass, I must have more than if I have 2 grams, right? Because I'm measuring how much mass is there. It depends on the stuff. Yellow, though, would be an intensive color or intensive property. Color is just intensive. It doesn't matter how much you've got. It's always going to be yellow, right? So when we're looking at sulfur, we can look at the difference between the two. Extensive depends on how much matter is present. Intensive does not depend on how much matter is present. Now, that's important. So like the density of an object doesn't matter, doesn't change whether or not you have 1 gram of the object or a billion grams of the object. Another one is boiling point, right? So if I want to boil water, I have to get it to 100 degrees Celsius. It doesn't matter how much water I've got, it's just got to get to 100 degrees. The amount of matter will definitely determine how much energy is required, right? If I want to boil the water in this beaker, well, it's not going to take that long. It's not going to take that much energy. If I want to boil all the water in the ocean, well, I still have to get it to 100 degrees Celsius either way, but it's going to take a whole lot more energy to get to 100 degrees Celsius for the ocean than it is for my little beaker. So an intensive property does not depend on the amount of matter present. Make sure you know intensive versus extensive properties. Be able to give an example, identify, which is which. Over here on the right, this is called a density column. You can see the most dense things are on the bottom, the least dense things are at the top. And again, it doesn't matter how much you put in there. If you made that with a gallon of each of those substances compared to this little 10 milliliter sample, really wouldn't matter. Okay, you'd still get the same column. Look through these properties. You don't need to know them all. You don't need to have like a memorized definition, but read this slide. Right, it came out of your book. Make sure that make sure that you've at least been exposed to them. Big ones that we'll talk about throughout the year: ductile or ductility, the malleability or being malleable, and conductivity. Those goes with metals. Okay, so both heat and electrical conductivity are characteristics of metals, as are malleability and ductility. Malleability means you can hammer something into a sheet. So think about hitting it with a mallet, like a hammer. Ductile means you can pull it into a wire. Okay, so just look through these, make sure you've read them, make sure that they're familiar to you. The reason we want to look at those properties is we want to be able to differentiate between a physical property and a physical change, and a chemical property or a chemical change. So physical properties, you can observe those without changing the chemical identity of the subject. So melting and boiling points are physical properties. When you boil water, you make steam, but the chemical, formula for water is H2O. The chemical formula for steam is H2O. Steam is still water. So you can find the boiling point without changing the chemical identity. It's still water. Physical changes are changes that, don't change the chemical identity. So boiling would be a great example of that. So is melting, cutting, or grinding, separating, tearing. If you tear a piece of paper, you still have paper. You didn't change it. So that's a physical change. Chemical properties and chemical changes come about when they undergo a change. So if I want to look at something like volatility or the ability to oxidize something or combustible, characteristics of a compound, I have to burn it or I have to, react it with something. So if you're measuring a change or a property and you have to do a reaction, well, chances are it's a chemical reaction or a chemical change. When you look at chemical reactions, and hopefully this is review from biology, remember that the yield arrow always points towards the products. Usually we write them left to right, reactants on the left, products on the right, but we don't have to. The arrow always points at the products. So if we flipped that arrow, but we didn't flip where the ammonia was or where the ammonium chloride is, then we would have reactants on the right, products on the left. That's fine, but just remember the arrow points at the products, okay? And typically we write reactions left to right. And when we look at chemical properties, there are a lot of them. There are a bunch of common ones listed there, things like reactivity or toxicity, flammability, and they usually have their own codes. Now, these codes up here I have are in Spanish, but fortunately the visuals that go with them are usually pretty easy to figure out, right? So one that everybody knows is the toxic one, right? So, hey, don't eat that. One that may be, less, I don't know, what's the term? Less, or not as easy to figure out right away is the exclamation point. The exclamation point means that it will irritate the skin, okay? But the explosive one, pretty easy to figure out, right? The dangerous to the environment, which has a dead tree and a dead fish on it. Yeah, don't dump that down the sink, right? So chemical properties have to do with how they interact with other things. Physical properties are things that you can measure without changing the chemical itself, right? Now, when we look for chemical changes, there are some clues that will alert us to the fact that, hey, there's a chemical change that has occurred. Number one, if you make bubbles, okay, so, most people have probably done the volcano, with baking soda and vinegar, produces a lot of gas. If you're creating bubbles, chances are, well, actually, if you're creating bubbles, you have made a chemical reaction. You can't say always, because someone always goes, well, what about boiling? Boiling makes bubbles. Well, okay, yeah, but you didn't mix two chemicals to make those bubbles. You just added heat. So bubbles generally indicate a chemical change. If you have a color change, so this second reaction here, this one labeled B, we'll actually do this in class. You mix two clear chemicals and all of a sudden you get this vibrant yellow. Okay, there's been a color change because the color of a substance changes based on what chemical it is. Color is dependent on the configuration of electrons in a compound. If you release heat or light when you do a reaction, there's a chemical change occurring. And then on the end, if you're using an indicator and your indicator changes color, so that's phenolphthalein, which is used to indicate the presence of a base. If you add acid to that and the indicator changes color, hey, well then your base has gone away. You've neutralized your base. So a lot of different ways that you can identify a chemical change is occurring. Bubbles, color change, heat and light. Now, on a book that I used to use, this was the picture on the cover, and it's showing, a color change, right? You can see right here, this mercury oxide is going from red to, you can barely see a little bit of silver there, a little bit of silver there. We've definitely produced bubbles, okay? We've got steam being produced. This is an extraordinarily dangerous reaction. I don't know why in the world they put it on the front of a, textbook, because you're heating mercury oxide in an open test tube. It's producing oxygen gas, which is flammable, and you're being left with elemental mercury, which is a toxin in the bottom. So not really sure why in the world they were putting that on the front of a textbook, but it's a good example of being able to spot chemical changes occurring right there, just using your observational skills. All right, so that's chemical and physical changes. So last couple of things we're going to talk about. We're going to look at the periodic table. We're going to spend a lot of time talking about the periodic table, okay? But just to make sure we have some basic understandings of where things are, all right? Number one, everything up here in yellow is a non-metal. Everything in blue is a metal, okay? And these little staircase right here are the semi-metals, okay, or the metalloids. You can see that there are a lot more metals in the universe than non-metals, okay? The vertical columns are called groups or families. They have common characteristics in common with each other, okay? And as you go left to right, you find that those characteristics repeat every now and then or periodically, which is why we call it the periodic table. Like I said a moment ago, the vertical groups are called families. A horizontal group is called a row or a period. And when we look at the metals, the nonmetals, and the semi-metals, we usually group them together. Hydrogen is an exception. You can see hydrogen here in the top left. It's yellow, but it's on the metal side. It sometimes acts as a non-metal. It sometimes acts as a metal. We'll learn how to figure out which it's behaving as, but it's kind of its own thing. It's special. When we look at metals, we find that all of them are solids at room temperature except for mercury. They are malleable, which means, like we said a minute ago, they can be hammered into a sheet. They're ductile, which means they can be drawn into a wire. And the majority of them are good conductors of heat and electricity. So here we have some metals. We have gold and copper, and there we have mercury. Non-metals are opposite of metals, right? So, they're poor conductors of heat and electricity. That's usually how we define them. Most are gases at room temperature. And if you can find them in the solid form, they're not very strong. They're quite brittle. So on the left here, we have chlorine gas, phosphorus in the middle, and sulfur there on the right, and we'll look at some sulfur in class. The semi-metals are kind of like metals and kind of like non-metals. They are, usually solids at room temperature, but they usually have very low melting points. So gallium, number 31 there, I have some gallium we'll look at in the class. If you hold gallium in your hand, it will melt. So it's got an extremely low melting point. And gallium and indium are in the same family. And if you take gallium and indium and you press them together, just that friction is enough to melt the two together, and they'll refreeze and make an alloy. So, they have some wild characteristics there. Most or all are semiconductors of electricity. So things like silicon we use in computer chips. And I also think germanium can be used in, I was just checking the periodic table on the wall. I think germanium is the other one that finds its way into computer chips. So semi-metals are pretty useful. Now, there are some special groups. We're going to learn their names. Group 18, which is all the way on the right, it's the 18th group, are the noble gases. They are entirely unreactive or inert. I-N-E-R-T means unreactive. Right next to them to the left are the halogens. They're group 17. They are extremely reactive. So you have really, really, really reactive right next to the really unreactive. On the left side of the periodic table, group 1 is the alkali metals, which are really, really, really reactive. They're very volatile. And group 2 are the alkaline earth metals, which are called the earth metals because we usually find them in the Earth's crust. Okay. Here's where they are. So we have the alkali metals and the alkaline earth metals on the left two most groups. On the far right, we have the halogens and the noble gases. The big, gigantic block, rectangular block in the middle that goes from row 3 to row 12 is the transition metals. And below that, kind of stuck down on the bottom, you have 2 rows of elements. They are the lanthanide metals and the actinide metals. The lanthanides follow lanthanum, and the actinides follow actinium. Okay, so that's introductory chemistry. Thank you for bearing with me. I know this is a long video. Anytime we finish a PowerPoint, there are usually some central questions on there. Not always, but often. If there are central questions, make sure you can answer those central questions. Okay. In this case, we have 2 slides, 1 through 9. Make sure you know the things on the central questions if they're there. Okay. Some other things you probably noticed as we've gone through this. A lot of my slides are color coded. Red text is super important. Blue text is usually like a definition or something like that. But make sure you definitely know anything that is color coded, red and blue. Okay, so just as we kind of page back up, you'll see those things. All right. I know that was a long slide, set of slides. Remember, as I make these videos, you need to watch the part that you didn't get in class, and then you can rewatch the part that you got in class if you need a little reinforcement. Okay. If you have questions, shoot me an email or message me on Remind, and I will certainly give you a hand. So see you guys soon. That's all we've got for today.